Redox reactions. Redox is a short term for what's called oxidation reduction. Oxidation reduction is the process of the movement of electrons. One cannot occur without the other. For this to happen, one species, chemical species, element, needs to lose electrons. And then another species or element will gain those electrons that were lost. Oxidation is the loss of electrons, and that's what we're going to focus on here in 1201. The gain of oxygen, we're going to focus on that in 1211 during our organic reactions because it makes it a lot easier. All right, so right now with inorganic reactions, we're looking at the loss of electrons. Reduction is the gain of those electrons from the species that was oxidized, or it's the loss of oxygen. Again, we will focus on oxygen when we move to 1211. For these to occur, we have to have something that spurs that reaction forward. It's not just, okay, some reactions can be spontaneous and just happen, but for the most part, there needs to be kind of like a kickstart. We have what are called oxidizing and reducing agents. A reducing agent causes reduction to occur. So it's like, I need reduction to happen. So I'm going to be the agent that is going to cause that. But for reduction to happen, I've got to be oxidized. And then the oxidizing agent saying, hey, I want to gain those electrons. I want to be reduced. So I'm going to cause oxidation to occur. Hence, oxidizing agent. They work together. We saw this graphic previously, but giving you what oxidation and reduction is. So here we have species A has got, it's an ion, and it has those electrons, whereas B is neutral. A is going to lose those electrons to B to help us understand this. And so I have Leo goes grrr. I'm a Leo. So lose electrons, oxidized, gain electrons, reduced. Ion A is going to lose its electrons. So it's going to be oxidized. And when it loses those electrons, it's going to form a neutral compound. Whereas B is neutral, it's going to gain those electrons, so it's being reduced to form an ion. A cannot just go from an ion to neutral. Those electrons have to go somewhere. Ionizing radiation is when electrons just get chucked off into the surrounding, and we don't want to be ionized because that can cause health issues and all sorts of things. So it has to have both. Another mnemonic is oil rig. I like Leo goes grr in 1201 because we're talking about electrons. Oil rig kind of doesn't make as much sense. But oxidation is loss, so we had to lose something, electrons. Reduction is gain. We had to gain something, electrons. All right, so we always have to have one or the other, and it's tracking where are these electrons going. With the reactions that we have talked about, here's looking at the electron movement that has occurred. Looking at this first one, we have our species, those are the chemical species or the elements, the process that's going to occur, and then the result. So looking at this first reaction, I have a neutral metal with a neutral nonmetal. What type of reaction has these species? Combination or synthesis? So what happens is we are forming one compound at the end. And in this compound, we are going to have ions. So we're going from neutral species to an ion. Metals lose electrons. Therefore, they are oxidized to form the cation in that compound. Nonmetals gain those electrons that were lost by that metal to form the anion in that compound. So if we have sodium and we've got chlorine, sodium being pure is going to give up one electron to the chlorine. And so it's going to go into the formula that sodium has lost one electron, the chlorine has gained that electron. Now the electrons are going to balance just like we do with everything else, so we need two sodiums. Each sodium donates one electron to each of the chlorines there to create sodium chloride. So the number of electrons that move is part of that balancing process to make sure the correct number of ions have been made. All right, so that is our combination reaction. In the next one, we have decomposition. So we have a cation that is in a compound and an anion that is in that compound, and they're going to split apart into their neutral states. So a cation that is positively charged to become neutral needs to gain negative electrons. So it's going to be reduced. The anion that is negative needs to lose those electrons to become neutral. Therefore, it is oxidized. It is giving that cation its elements. So an example is if we have HGO, mercury is going to have a +2 charge, oxygen has a -2 charge in this formula. When we get our products out of this, we have pure mercury, so that's neutral, and we've got pure oxygen, that is neutral. So oxygen had to donate its 2 electrons to mercury to become neutral on either side. Again, we have to make sure that it is balanced. So this is going to occur twice for the 2 oxygen that need to be there for that balanced reaction. The third one is our single replacement reaction. We have a metal that is neutral, and then we have a cation that is in solution. The metal wants to be a cation because it's stable, and it's going to force that cation to come out as a pure substance. This is really cool. This is how we can isolate metals that are typically not easy to access, like sodium. We do this process right here. We force it out of solution. The metal wants to lose electrons so that it can become a cation that is now in solution. The cation that is currently in solution is going to gain those electrons to become the pure metal at the outside. So here, if we have pure sodium, and in solution, we've got lithium chloride. And so lithium has a positive charge, chlorine has a negative charge. Sodium wants to be the cation. So sodium is going to give lithium its electron so that it forces lithium to come out as a neutral element. So lithium comes out as a neutral element, and sodium now becomes an ion in solution. And so those are the different ways that these processes can take place and how they support and explain these chemical reactions that we have been talking about. When we're looking at redox reactions or synthesis, decomposition, single replacement, or combustion, we want to be able to understand how can we manipulate these reactions to do what it is we need. To do that, we need to understand how the reaction takes place, what is going on, where electrons are coming from, and where are they going. In order to understand that, we start to break these reactions apart, and we break them out into what are called half reactions. In these half reactions, we can then see species that are oxidizing or losing their electrons and species that are being reduced or gaining those electrons to help explain how bonds are made, broken, transitioned, any of those. Using this reaction, we have magnesium reacting with oxygen to give us magnesium oxide. So we want to show the electron transfer between the 2 chemical species. Before we can write these half reactions, we want to know what's kind of going on. So we're going to start with what's called the oxidation state. The oxidation state is just the charge of the element in the position in which it is. When we are looking at magnesium, it is an element, so its oxidation state is neutral. Oxygen is an element, its oxidation state is neutral. Now we're in an ionic compound, therefore it has ions. Magnesium has a positive 2 oxidation state because it's got a 2+ charge. Oxygen has a negative 2 oxidation state and it's got a negative 2 charge. What we need to notice is that magnesium goes from neutral to a +2. Electrons are negative. So if your species that's going to become positive, you are going to have to lose those negative electrons. So that means if they lost those electrons, Leo goes Gur, lose electrons oxidized. Our magnesium species is oxidized. Oxygen is going from neutral to -2. So it's gaining negative charges. So it's going to, that is gain, I promise, be reduced. Looking at what these species are. Our oxidized species, magnesium. So here we have magnesium. It's going from a neutral to a +2. This means it loses 2 electrons per magnesium within this reaction. Oxygen goes from 0 to -2. That means each oxygen has to gain 2 electrons in this reaction per oxygen. Then we have this term called spectators. Spectators are ions that do not participate in the redox reaction. Spectators are only going to occur in single replacement reactions. Because synthesis and decomposition is typically only working with 2 ions and not 3, we don't have any of those spectators. So there's none right here. Now, looking at our half reactions, we want to look at what's happening to magnesium, what's happening to the oxygen. We have to make sure that these stay balanced. Looking at our magnesium first. So magnesium becomes oxidized. To do this, it needs to give off electrons. So magnesium is going from its neutral to its charged species. We have 2 sets of magnesium. Each magnesium gives off 2 electrons. So 2 times 2 tells me 4 electrons are in play. So now we want to go to the oxygen side. Oxygen as a pure element is going to go from O2 to just an O with a 2 negative charge. That O is in a compound. The subscript 2 did not transfer with it. That is how we balance the reaction. So we have 2 oxygen ions in that reaction. Sorry. Goodness gracious. I've got this. So to have each oxygen atom become a negative ion, they have to gain the 4 electrons that were provided from magnesium. So these are the 2 half reactions. The magnesium is the oxidation half reaction. The oxygen is the reduction half reaction. To check your work, what you want to make sure happens is you have the reaction that is written above. All right, so we want to bring down everything that just occurred. We have 2 magnesium plus oxygen plus 4 electrons. We have 2 magnesium ions and oxygen ions. They're just in their ionic compound, and 4 electrons. We want to cancel out anything that repeats because those 4 electrons are the same 4 electrons that oxygen had. So they need to be the same number so that they can show that full transfer. So these half reactions are showing us the number of electrons that need to be present in order for the transfer to occur so that the ions and atoms are where they need to be.